Good afternoon, Mr. Fugit here. Today in our video, what we're going to be looking at is the last part of our graphical kinematics practice sheet, which we covered in class. Here we're specifically going to be answering question number 10. I did want to make a separate video for this problem because it can be a little bit lengthier in nature, and it's a very specific type of problem that will ask us to do several things to get to an answer. So I am going to be referencing back to the graphical kinematics practice. This is a continuation from videos 1 and 2. This is the third part, so if there's anything that you see us reference in this video that you don't see, fully explained here, feel free to reference back to videos number 1 and 2. So we are going to be looking at the last question, which relates to our velocity versus time. Again, we are going to pick up with what we previously answered in question 9 as we move on to question number 10. So in question 10, here's what we are looking for. Does the object ever return to its original position? Justify your answer showing your work. So here, we're asked about, do we get back to our original position? So remember, if we're looking for the position, but we have a graph of velocity versus time, that means we need to find the area under our curve. Now, because we're not told a specific time value we're looking at, it says, does the object ever return? We're going to have to look at all of the area under our curve to see what our object is doing. Now, if we come back to our picture, it's a little bit jumbled here. In the last video, we saw for the position after a time of 3 seconds. We divided our areas into a triangle here. I'm going to call this shape number 1, and a rectangle here, we'll call this shape number 2. Now, what we have so far is an area for shapes 1 and 2 together that is 2.5 meters. I'm going to go ahead and erase that work so that our picture is a little bit more clear. Again, if you want to see me solve those, go back and reference video number 2 for the graphical kinematics practice. So I'm going to erase what we have. What I am going to do, however, is I'm going to jot down those values. So from a time of 1 second out to 3 seconds, or really I should say 0 to 3 seconds, our area was 2.5 meters. Now, because all of that area is positive, that means our object is just moving in the positive direction. So we need to go ahead and find the rest of our area in order to figure out what our object is doing. Now, we have kind of a weird looking shape from 3 seconds on out to 6 seconds. So we need to break this up a little bit. There are a few ways we can do this. One thing I might do is I'm going to make this shape right here a large triangle. Then I'm going to make a small triangle up top. And then I'm going to make one more rectangle. So there are 3 more shapes that we're going to look at. I'm going to call this shape 3, the next blue rectangle. I'll call this triangle shape 4. And then I'll call this small triangle in here shape number 5, just so we can keep track of all of our areas. So we'll say area 3 is going to be a rectangle. We have a base of 2 seconds from 3 to 5 and a height of 1 second. So a height of 1 meter per second. So 3 seconds times 1 meter per second. Well, 3 times 1 is just going to give me 3 meters. So that is our area for shape 3. We'll look at shape 4. That is a triangle. So 1/2 base times height. 1/2, our base here for the triangle is 5 to 6 seconds, so just 1 second. And the height here from 0 up to 2, so 2 meters per second. So 2 times 1 gives me 2, multiplied by 1/2. That's going to be 1 meter. And then area 5, we're kind of spread out here. Area 5, that is another triangle, 1/2. The base here is from 4 seconds to 5 seconds. You might need to look at that a little bit more carefully. 4 to 5 seconds is a base of 1 second. The height, here's where we have to be careful. The height starts at 1 and goes up to 2. So from 1 to 2, that's only a height of 1 meter per second. So 1 times 1 gives me 1 times 1/2. This is just going to be 0.5 meters. So now, all of those areas added together, 3 and 1 and 1.5, give me a total area of 4.5 meters. So I'll come back to what we've already written down. So from 0 to 3 seconds, we travel 0.25 meters. From 3 seconds to 6 seconds, our area is 4.5 meters, right? I'll double check our values real quick. Let's double check. Come back. 2 times 1. Yeah. Oh, you know, I realized I did make a mistake here. As I come back and realize, from 3 seconds to 5 seconds, this is just an area of 2 seconds times 1 meter per second. So 2 times 1 should be 2 meters. I felt like I made a mistake there. So 2 times 1 gives me 2 meters. So 2 and 1 is 3, plus 0.5 is 3.5. Okay, so again, I did make a little mistake there, but good thing that we did catch it. So from 3 seconds to 6 seconds, our total area is not 4.5 meters, it's actually 3.5 meters. So now we have all of our areas under the first 6 seconds of our curve. So 2.5 and 3.5 give me a total of 6 meters, which means during that time interval from 0 seconds all the way out to 6 seconds, I travel a total distance, or displacement, we should be more specific here, of 6 meters. Okay? Now, the question is, do we ever return back to our original position? How do we know that? Well, if I look back at my graph, at a time of 6 seconds, I then begin moving in the negative direction. So I start traveling opposite from where I began, which means maybe if we cover enough area, I'll get back to where I started, maybe I won't. But now we need to look at what are my negative areas and see how those compare to my positive areas. So again, I'm going to erase what I've done here, just so we can clean up our picture a little bit. So I'll erase our areas. I'll leave the breakdowns that we have. Okay, so now I need to look at my negative regions. So got kind of a weird looking shape here, so here's what I'll do. I'm going to go ahead and break this down. I'm going to draw a line from my curve back to the time axis. Okay, so it looks like we have here, I can make maybe a rectangle on the left-hand side, a rectangle on the right-hand side, and then maybe triangle on the left and the right, losing my shapes there. 2 triangles, left and right, and a rectangle in the middle. So I'm going to call this a triangle on the left. We'll call this area 6. The rectangle in the middle, area 7. And the the triangle to the right, I will remember that, area 8. Now you can probably see area 6 and area 8 look like they're about the same shape, right? A triangle with approximately the same dimensions. So area 6 is a triangle, 1/2 base times height. So 1/2, our base there is just 1 second, whether it's from 6 to 7 or from, looks like 7 to 8, 8 to 9. So a base of 1 second, and here's where we have to be careful. When we start at a height of 0, we go down to -2. So we have a negative height, which means we're at -2 meters per second. So -2 times 1 gives me -2, times 1/2 gives me -1 meter. Now you're probably thinking, how is my area negative? I've never seen area be a negative value. But remember, this isn't the area of an actual physical triangle. This is just a shape we're making on our graph. So the fact that our area is negative just means our object is moving in the negative direction. So we're going to assume area 6 and area 8 are both the same area, -1 meter. Now area 7, our rectangle, we'll solve over here. We can simply take base times height, because it is a rectangle, or side times side, length times width, whichever whatever we call those dimensions. Our base here is 1 second. Our height is -2 meters per second. So base of 1, height of -2. So 1 times -2 gives us -2 meters. That is going to be area 7. So in total, -1, -1, -2 gives us a total area of -4. So after we hit 6 seconds, so that looks like it was from 6 out to 9, just so we understand. Here we go. So from a time of 6 seconds to 9 seconds, our area is negative 4 meters. So here's what that tells us. As we're moving our object, whatever our object is, we travel out 6 meters, but we only come back 4 meters. So if we were moving in a straight line, it would look about like this. We start at some initial position, I go out 6 meters, we'll call that a positive 6 meters, and then I come back 4 meters. Do I return back to where I started? Well, no. In order for me to return back to where I started, again, obviously not drawing the scale, in order for me to return back to where I started, I would have to travel at least 6 meters in the negative direction. So if my area in the negative direction was -6, or even something greater than that, -7, -8, -9, as long as I travel a greater distance in the negative direction than the positive, I would hit my initial position. But because I only travel 4 meters back, I can't come back to my original position. So overall, our answer is going to be no, and our work is our justification. My area in the positive direction is greater than my area in the negative direction. Now, if I come back to my picture, you'll notice there is this last little triangle out here. That last little triangle represents an area that is going to be positive, because during that time interval, we're moving in the positive direction, a velocity that is greater than 0. Now, all that's going to tell us is, in terms of our actual movements during this scenario, after I travel the 6 meters in the positive, the 4 meters in the negative, I'm going to travel some other distance in the positive. Now, it doesn't really matter what that distance is for the sake of this question, because since it's going back to the right, it's not going to lead us back to our original position. Okay? If we did want to find that area, we could. It's a triangle, 1/2 base times height, but for the purpose of our question, that's not really what we're interested in. So hopefully, in looking through these videos, this gives you an explanation of what we're doing with graphical kinematics. Position versus time graphs, which we can read directly to find position, and using our slope to find our velocity, and velocity versus time graphs, which can tell us 3 things. Directly our velocity, using slope we can find acceleration, and using the area under the curve, we can work back to find our position. You will deal with some of these problems on your homework, and they may or may not show up on the exam. So make sure you feel comfortable with what we're doing with our position and velocity versus time graphs. Good luck.